So, welcome back. In the last class, whatever we were discussing about is PIV, and we have discussed about the measurement principle and the operating principle, then how to process the PIV images to get the velocity map. So, whatever we have discussed about the PIV reconstruction algorithm, we said that what we do in this kind of in PIV, we take two images in a very short duration, we kind of divide the images in a small pixels, and then in each pixels we do the FFT for both the pixels for both the time, and then we cross correlate both the images, and based on the cross correlation we do the inverse FFT and try to find it out the overall displacement. So, from that displacement we get a displacement peak, and once you have the x and y location, you can calculate the Vx and Vy by delta x by delta t and delta y by delta t. So, this was the reconstruction principle of the PIV. This is a very good technique. It can have a very high temporal resolution, very high spatial resolution, and it can be used for kind of it don't disturb the flow, and it can be used for many of the systems. So, but there are certain factors which affect the accuracy of the PIV experiments, and one of the factor is that laser intensity, that what is the laser intensity and laser energy and you are using, and laser wavelength, because whatever you are going to do, you are going to form a seat of the laser, your particle will get illuminated because of that, and your acquisition is based on that how fast your laser is generating the pulse. Further, again as I discussed earlier, that this is a optical based technique. So, your laser light penetration, what depth you will able to measure in a 3-dimensional column will depend that what is your energy of the laser. So, if your energy of the laser is low, you will not able to penetrate through the longer distance. So, one need to be very careful about that. Then the second important thing is the tracer particle. So, first we will discuss that whatever was the component we require in the PIV experiments to do the PIV measurements, and then we will try to see that what are the critical elements. So, definitely the thing which we require is a tracer particle or seed particles, okay, which you are used to seed the flow, okay, and which will be illuminated in the presence of the laser light. Then you need a laser source and laser seat optics. So, you will have a laser again as I said that laser energy, laser wavelength is very critical for the PIV measurement, and depending on the application you have to use a suitable energy as well as suitable wavelength. If that is not there, your data will be noisy. So, that you need to do. Then you have to generate you need a seat optics which will be generate a sheet of the laser. Then you require a camera, again depending upon what type of PIV you want to do. If you want to have a time resolved PIV, okay, that is called time resolved PIV, and this is very famous nowadays. You need a very high speed camera. Okay. So, what you are going to do, if you want to see that how the flow is resolved with the time, it means with the time how the things are changing, and as I said that in multi-phase flow the time resolved PIV is more applicable, because multi-phase flow the things changes with the time with the location. So, if you do not do a time resolved PIV, you will get the velocity vector, but you will not able to get that how this vector is changing with the time, particularly for a condition where the flow condition where velocity is very high. If the velocity is very high, the change in the flow will also be very rapid. So, in that cases you need a time resolved PIV. In the time resolved PIV you use actually a CMOS camera, and this CMOS camera is generally a very high speed camera which will be operated at a very high frame speed, say the rate of 1000 or 2000 or 4000 frame per second. So, you require you get the kind of photographs at a very high frame rate, and based on that if you get it that you can analyze the images, and then you can get that with the time how the velocity field are changing. So, the time resolved PIV is there, or if you do not want a time resolved PIV, then a CCD camera, normal camera kind of this charge coupled device, it is called CCD camera, can be used. Definitely CMOS camera, which is high speed camera, is costlier compared to this CCD one, but you can do that high speed imaging with the CMOS camera. In the conventionally we use CCD, which is charge coupled device camera. So, the camera is very critical. In the camera you have to see that what should be the resolution of the camera, what is the interrogation area you want to investigate. So, based on that your camera focal this, and you have focal length, your shutter speed, and all those parameters need to be changed. You have to buy a suitable lens so that you can zoom the camera on a particular spot, or you can have a kind of, if you want to have a bigger interrogation area, then you have to keep the camera a little bit far from the surface, so that you can cover the entire range. So, depending upon the application, you want a complete map, you want a very small zone to be focused, you have to buy a suitable lenses, you have to maintain the camera, you have to keep the camera at a certain distance from the location, so that you can do the focus. Okay. So, based on that, the camera requirement is also very critical. You need to have a camera which should be very good, where the if you are operating in the, if you are not doing a time resolved PIV, your shutter speed should be very high. If you are using a high speed PIV or time resolved PIV, it's the camera frame speed and resolution should be very high. So, that is the camera requirement. Then you have to do the measurement settings, okay, that you have to set the laser seat, you have to fix the camera and all. For that you need the settings, okay. You need the supports, you need the isolation table which can remove the vibration if there is any vibration there, and then you have to have the interrogation area you have to do, and then you have to select a suitable area that where you want to focus, and then you have to use a post processing software to get the velocity field. So, that post processing software will do the same job as we have discussed. You can write your own code, or you can use a software, commercial available software for the post processing. So, these are the major component. Out of this component, definitely the tracer particle, light source, seat optics and camera, these 4 are very critical. These 4 are very critical, and the accuracy of the PIV will depend on these 4. Okay. So, in that light source we have already discussed. Seat optics is something which you have to make the seat, okay, that should be very good, synchronized properly. Your seat optics and your camera, your laser should be synchronized properly, so that you get the photograph at the right time. The camera speed should be very high, or very good resolution you should use the camera. So, that is there, but one of the major, from flow perspective, one of the critical parameter is the tracer particle, that what type of tracer particle we should use. And as we already discussed earlier during the introduction classes, that if your tracer particle is not of the right size, then what will happen? It will have its own motion. So, if I say that the response time is say very low, then it will follow the path of the fluid. If the response time is very high, then what will happen? It will actually have its own motion, it will not respond to any change in the fluid flow. So, the tracer particle preparation is very critical, and as we discussed in the LDA also, that in LDA what we do, we put the laser beam on the particle and we measure that the scatter light, the light is scattering. Here also it is the same thing approximately, you are using the laser light to illuminate the particle. Now, if the particle size is very small, then the illumination will also be very small, the scatter will be very small, and in that case it is very difficult to record those particles on camera. If the size of the particles is very big, then illumination will be high, but it will not follow the path of this particle or part of the fluid, sorry. So, in that case one has to be very choosy, one have to be very selective while choosing the tracer particles. Some of the particle which is widely used to map the gas and liquid by PIV has been shown here. So, for gas generally we use the polystyrene particles of a size 0.5 to 10 micrometer. For aluminum, we can also use the aluminum particle of 2 to 7 micrometer, sometimes we use magnesium particle of 2 to 5 micrometer, and we also use some oil droplets of 0.5 to 10 micrometer to track the air. So, that these are used as a seed particle. So, either it can be a small tiny oil droplet, it can be a very small polystyrene beads, it can be aluminum bead, it can be magnesium bead of different sizes. Okay. Now, what is the good thing? If you see here, the particle sizes are very small, we are talking in the range of 0.5 to 10 micrometer maximum. Okay. So, why the particle sizes are very small here? The major reason is that this air have a the refractive index difference of the air and the particle, or the gas and the particles are very big. Okay. And therefore, the small particle can also do the same refraction as the small particle can also give a refraction which will be more than the air. Okay. So, in that case you will get a proper contrast. Okay. So, in what will happen, that they will give more refraction, they will be white bright color, the air will come or the gas will come as a dark color. So, refractive index, because they are very different, okay, compared to the solid and gas, and that is the advantage, and that is why you can afford to have a very small size particle. While in case of the liquid that is not true, and that is why you need to increase the size of the tracer particle. Generally we use polystyrene, and if you see the polystyrene sizes, now we are using 10 times higher. It is 10 micrometer to 100 micrometer in the range, so that you get the more refraction, your image quality is better. Okay. Or we can use a glass beads of 10 to 100 micrometer. Aluminium also can be used, which is in the 2 to 7 micrometer, because there the refractive index is different. So, if you see this, generally the gases, the particle size is very small, you can afford to do that because of the difference in the refractive index. In the liquid, you need to increase the particle size. Now, once you are increasing the particle size, one need to be very careful that your Stokes number is still very low, or you can say the response time of the particle is very low and it is following the path of the fluid. One need to check that. One way to check that is to calculate the response time, or you can solve the complete Bassett-Bosnes-Oseen equation, BBO equation known, and you can see that how much extra error you will generate if you are using a finite size of the particle which diameter is little bit bigger. So, those exercise need to be done. Now, this is whatever I said, that what is the performance, where what you should choose smaller particle or larger particle. As we discussed that if the particle is small, there is a 3 parameter on which we discuss it. We discuss based on that how good it is following the flow, how good it is doing the light scattering, and if there is any change in the velocity, in the fluid velocity, how well it will respond to that. So, in that 3 parameter, if a small particle you are using, definitely it is going to follow the flow in a bigger good way. Only thing is the particle should not go on the Armstrong level, that the Brownian motion start dominating, it will have its own say again. So, till you are making sure that you are not going in the Brownian regime, if the smaller the particle, for the flow perspective it is good. But as we discussed, the flow is the smaller the particle, lesser will the scatter, and in that case the light optics wise, the image quality wise, it will not perform very good, and that is why I will give a bad rating for that, that the smaller particle is not good for the imaging purpose. And again, because it is responding to the flow very well, if you do any change in the flow, it will respond it better. So, that is the way. If you go for the smaller particle, you can be assured of follow of the fluid, that it is going to follow the fluid. Any change in the fluid velocity, it will respond immediately. The only thing is you have to careful is with the image quality. So, what you need to do? You have to increase your laser light intensity, okay, so that your image quality becomes little bit better. Okay. So, that is drawback, because you have to use a high power laser. High power laser will create a safety concern too, and it will be very costly. And then if you use the large particle, definitely the chances that it follow the flow is low. It will have its own say, and that is why the follow the flow will be bad. It will not respond as quickly to change of the flow, and that is why the step response will also be bad. It will not respond that quickly, but the light scatter image quality wise it will be good. So, it is always a trade off, and depending on the application, the accuracy you want, the error you can afford, the laser power you can afford, the depth you want to investigate, you choose a suitable particle. Okay. So, this is the way you need to keep there in the mind, that if you are choosing the smaller particle, what are the error you are going to encounter, what are the problem you are going to encounter. If you are using a larger particle, what are the problems you are going to encounter. So, one need to be careful. If you are using larger particle, one need to see the response time or Stokes number of the particle and see that how fast it will able to respond to the flow. So, with this we have discussed about all the parameter of the particle image velocimetry. Obviously, there are several advantages of the PIV, even compared to the intrusive technique or invasive technique, and compared to the LDA. The most advantage part is that it gives the complete velocity map, whole field measurement can be done, while LDA was a point measurement. So, that is a major improvement which has been done from LDA to the PIV. You can get the velocity directions, you can get the velocity magnitude, everything you can get here, that what is the velocity and all. And because you are completing the flow, complete flow field, you can also get the recirculation cell structures if there are any forming in the turbulence or in multi-phase flow. You can get those structures, you can get the circulation cells and all. So, it can give you all these 2 parameters, it can give you completely. It can give you the instantaneous flow field map, it can give you the mean flow field map. So, whatever we have discussed in the introduction, what we require, it can give everything. If you are using a high speed camera, you can also find that how the instantaneous flow field map is changing with the time, how the fluctuations are changing with the time, all those things you can get there, or how the recirculation cells or structure dimensions are changing with the time. all those things can be done here. Then it can measure the velocity which is 0 or very close to 0. So, if a very low velocity is also there, it can measure it. There is no problem, like in HWA we discussed that when the velocity is very low, you cannot use the hot wire anemometers. Why? Because the heat transfer due to the convection may not be dominating, natural convection may also play a role, and then your whole calibration equation will be disturbed. So, in this case there is nothing like that. You can use it for even 0 velocity or very velocity which is very close to 0. It is very robust technique, and the velocity results obtained are very accurate or mostly accurate only if you are using the laser optics, proper seed particles and the camera. So, these specifications if you are able to manage, then your spatial resolution, your temporal resolution will be very high. Temporal resolution directly depend on that high speed camera. If you are using a very high speed camera, your temporal resolution will be even better. So, that is the advantage of this technique, but there are several disadvantages too, and as I said that the disadvantage first comes with the particle size and the length. So, definitely if you are doing that lens pulsing, because we do the pulsing of this, the pulsing of this should be, one should be very careful while doing pulsing the laser seeds, okay, or laser light. So, your pulse rate should not be very long, okay, so that it can actually should not be very long, so that the particle which we want to go out of the view, or it can go out of the kind of interrogation area, most of the particle if it is going out of the interrogation area. So, it should not be long enough, very long. It should not be very short also, that the particles are not doing any displacement. So, definitely the pulse light should be long enough to capture the displacement. It should be long enough that the particles move certain distance and you are able to capture those distance with the camera which you are using, the resolution of the camera. It should move such that the resolution of camera allow you to measure the displacement of the particles. And at the same time, it should not be the particle, this delay should not be short enough, so that the particle goes out of the integration area, particularly the particle which are moving in the direction of the laser seed thickness. So, they will go outside of the area or outside of the focus, and you will not get the image. So, what will happen? You will lose the particle between the two pictures, and that will hamper your accuracy. So, the laser pulsing rate should be very accurate. You need to be careful about that. Then you have to also see that the power of the laser. So, you need a very high power laser, so that you can reduce the particle size, as I said, but the high power laser, the problem is that it is very costly and there are safety issues also. Okay. And then the size of the particle should be small, or be small enough so that it can follow the path of the fluid. If the size of the particles is not correct, then you will get the velocities which is not the accurate velocity of the fluid. It will also have a say that how the particle is moving inside. So, particle will have its own size. Then the size of the area, interrogation area which we are using should be small, such that there is no significant velocity gradient within the area. So, if you are choosing a very big area, then what will happen? You will miss on the velocity field or velocity information. So, suppose this is your overall picture, and if you are using the interrogation area in this one case this, and in one case this, what will happen? In this case, the number of particles will be less. If the number image density will be less, as we said, we have already discussed that the accuracy will be less. But at the same time, if you use a very big area, then what will happen? The number of particles will be definitely increased, but there may be a velocity gradient within this area. And what we are going to do? We are adding all the particle movement and then giving one displacement. So, what will happen? You will lose on the spatial resolution. You will not able to get that whether there any changes there within that velocity, that area or not. So, therefore, the size of this should not be big enough, but it should not be small enough too. We should have a considerable number of particles inside, so that I can maintain an image density of between 10 to 15 at least. Okay. So, that is the again the limitation, that you cannot go for a very small, you cannot go for a very big. So, you need to be optimal. It can be, the major limitation is here, that it can be used only for transparent system. So, if your wall is opaque or your system is opaque, you cannot use this. So, once I say system is opaque, what does I mean? I mean that if suppose you are using a gas solid fluidized bed, where the solid particle fraction, bubbling fluidized bed say, the solid particle fraction is in the range of 20 to 40%. What will happen? All the laser light will be refracted from the wall. You will not able to form any laser seed. And if you are able to do any experiment, the experiment will be limited near the wall only. So, you will not able to get it. That same thing is true for a very high bubble fraction, say if you are operating a bubble column with a discrete bubble fraction of around 25 to 30%, again the same problem you will see, the bubble will refract the light, you will not able to form the sheets and you will not able to see through inside the column. Definitely the column where the wall itself is opaque, there is no question of using the PIV. So, this is the major limitation, and that is why the PIV again like LDA cannot be used for a discrete phase volume fraction more than 5. So, if you have a discrete phase volume fraction more than 5, your resolution will be severely hampered and you will be most of the time measuring whatever is happening at the wall. Okay. So, we discussed wall. So, what we discussed till now is about the optical based technique, which is LDA and PIV. The other also we have not discussed it, like I have touched upon the PTV, which is particle tracking velocimetry. These all are optical based technique, and each optical based technique, the major limitation is these two, that you need a transparent wall, you need the transparent system too. Once I say transparent system, it means the fraction of the discrete phase should be very small. Okay. So, that is the major limitation of all the optical based technique, and that is why the next generation improvement has been done and new techniques has been developed, which is based on the radiation, and that radiations are mostly gamma based radiation. We know that the gamma based radiations can penetrate almost anything, and the losses in the radiation will be very small till you are not using a very thick wall to stop all the radiation. So, in that way, that is the next phase of development, the radiation based technique, and in that technique mainly two techniques we will discuss. One is the positron emission particle tracking and another one is the radioactive particle tracking. So, what we do in the positron emission particle tracking, as the name suggests, that you are tracking the motion of a solid which is emitting a positron particles. Okay. So, what we do, we use a reactor of this kind. Okay. This is the typical picture which is taken from the Parker group, which is from University of Birmingham. We have taken it from his group photographs. This is Parker paper in 2006, which has been published, where they have investigated the Rotary clean by using the PEPT. So, what the PEPT do? PEPT actually track a motion of a single particle, single radioactive particle, and that radioactive particle is actually the source of positron emission. So, it tracks the motion of single radioactive particle, which emits positron. So, what it does, it emits the positron, and that we know that once a positron annihilates with the electron. So, if a beta plus, I will say, or E plus annihilates with E minus, it actually generates two back to back gamma rays. So, it generates the two gamma rays which actually moves back to back 180 degree apart, and the energy of this gamma ray is 511 keV. So, we are using a source, okay, using a solid particle which is a positron emission source. It emits the positron. Once it emits the positron, the electrons are available in the atmosphere or near about the system. They interact with them. Each annihilation generates two back to back gamma rays which are 180 degree apart of energy 511 keV. So, that what is being emitted. Now, this gamma rays which has been emitted coming from the particle has been detected by the series of scintillation detector which has been clubbed in a unit, and we call it as a gamma camera, or you can say positron camera, and they are nothing but they are scintillation detector, the array of the scintillation detectors. So, you place it in the detectors, okay, and each detector is able to find or kind of detect the gamma rays which are incidented on top of the detectors. About the detector we will discuss in the radioactive particle tracking technique, because these are the same detectors we are going to use. Here you use the array of bulk detector, there we will use the individual detectors, and we will say that the functioning, how the detector works, we will discuss during the radioactive particle tracking technique measurements. So, the series of detectors are placed which are actually recording those gamma rays which are coming back to back, and we have a data acquisition system which are recording only those gamma rays which is simultaneously detected on both the detectors. So, this is one detector, this is second detector. As we know that gamma ray will be emitted 180 degree apart back to back of the same energy. So, suppose this is the detector we have placed, there is a particle which is emitting the gamma rays. So, ideally both the detectors should get the gamma ray at the same time. So, only simultaneous detection we actually take it as a signal. If the detection is not simultaneous, we do not take it as a signal. Why it cannot be simultaneous? For some cases, because there can be some reflection or diffraction of the gamma rays because of the medium attenuation or medium kind of solids present, or the medium the things present or the object present within the medium. So, those things we neglect, we record only those gamma rays radiation which is kind of detected simultaneously 180 degree apart. Then we use the theory of triangulation to reconstruct the position of the particle. I will discuss what is theory of triangulation. So, what we get the Lagrangian track of the particle, we get that particle position. With time this positron particle will move inside the bed, and as the fluid will move, you will also get that position of the particle. So, you will get that Lagrangian position time series of the particle. So, you will find that how the particle position is changing with the time. Once you have the particle position, we acquire the data for sufficiently long time, so that we have a sufficient statistics involved, and then that is being used to calculate the velocity. How it has been done? That again the post processing part is other than the reconstruction of the particle is similar to whatever we are going to discuss in the radioactive particle tracking technique, and that is why I am not discussing that here. We will discuss it in the next class. So, those things remain same, and that is the major improvement if you will see, because we are using gamma ray, and because we are using gamma ray, we can use this technique in the real equipment system. And the photograph which I have shown here, which is from the Parker group, you see that the wall is made of SS. So, if you have a PIV system, if you have LDS system, definitely you cannot use it here, but because it involves gamma radiation, it can penetrate the SS, you can have the signal recorded with you, and this technique can be implemented. So, detail of the technique, again other than the inhalation part, the way the gamma ray has been generated, it is pretty much close to whatever we do in the radioactive particle tracking, and we will discuss it there. So, what we will do, we will discuss now that how to do the reconstruction. Okay. So, again to revise the basic, what is happening, that we are having a gamma ray, we have a particle which is emitting the positron, that positron is annihilating with electron, and it is generating two gamma ray which are back to back 180 degree apart, okay, and they are being detected on the gamma camera, or the camera being used, or the this detector network is being used to capture those gamma ray incidents. We capture only those gamma ray incidents which are simultaneously recorded on both the cameras or both the kind of detectors, and then we use the triangulation theory to calculate the position. Once we have the position, we do the experiment for sufficiently long time, and whatever you get, that while doing the experiment for sufficiently long time, you get that how the particle is moving with the time. From there you can calculate by delta x by delta t the particle velocity, and then you can use the same information to calculate the mean velocity, fluctuation velocity, and all the other parameters. So, about the post processing we will discuss later. We will discuss that reconstruction method which is being used in PIV, which is different from the RPT. So, these are the two photographs, both are from the Parker group. This is for horizontal clean, rotary clean, where you can see this is made of SS, and this is for the bubbling fluidized bed, where the same PIV experiment is being used, and this camera actually surrounds completely the zone of interrogation or the zone of interest where you want to do the measurements. So, this is about the PIV. For the reconstruction, what we do, the PIV reconstruction, as I said that you have two detectors. So, big detectors are there. So, suppose this is the two detectors, there is one positron, one electron, they annihilate each other. Once they annihilate each other, they generate two gamma rays which are 180 degree apart, back to back 180 degree apart. So, what will happen, both this will travel within the medium and reach to the detectors, and detector will actually record those incidents which is simultaneously detected. So, you will have this. Then similarly, what you will get if you do this detector, so you will get a line, okay, because now both are absorbing at the simultaneously. We know that one location is this, another location is this, you can connect it through a line, you will get a line. Similarly, several such kind of annihilation is going on for all the position, because the gamma decay. So, it is decay kind of, so decay, so radiation. So, the source decay happens at a very high rate, okay. So, that rate you are also doing the annihilation, and several such lines will be formed. So, say one line is this, one line. So, several such, suppose this particle is there, this is detector, if I see this is this is detector, this is also detector, the several such incidents will happen, this one line, then there will be another line, then there will be another line. So, several such incidents will be taking place, you will see huge number of lines, and wherever all those lines will cut, that will be the position of the particle. And why we call it a triangulation? Because the two line cut will give the position, the third line which will be passing through it will verify the position of this particle, that this is the particle position. And we do not use for 3 lines, we use several lines, considering that how the particles are cutting, and all the lines will cut actually at the same location, and that will give the position of the tracer particle. And then similar thing, similar phenomena can be repeated for the longer time with the longer duration of experiments, and you can find it out that how the tracer particle is changing with the time. You can acquire the data at a very high frequency up to 100 hertz, not as high as the HWA. You can acquire here up to 100 to 200 hertz, and you can get that how the position of the particle is changing with the time. So, this is the reconstruction approach is being used for the positron emission particle tracking, and then in this reconstruction you get after this that how the particle position is changing with the time. The other post processing remains same, we will discuss in the next class when we will be discussing about the RPT post processing or radioactive particle tracking post processing. Okay. So, that is the overall advantage. Currently what is happening, that the tracer particle down to 100 micrometer particle you can use, you cannot use a very small tracer particle because you have to re-radiate it, make it a positron emission source. So, generally the particle in the 100 micrometer range is being used. You can locate the particle within 1 mm range, okay, and 1 millisecond time. So, that is the maximum temporal resolution you can get and maximum spatial resolution you can get. Definitely this resolutions, spatial resolution and temporal resolutions are lower compared to the PIV and LDA experiments, but major advantage of this is that it can measure the flow in an opaque system of a very dense system, or where the discrete phase system, discrete phase fraction is very high. That is the major advantage. The another major advantage, and that is the advantage over the radioactive particle tracking technique and the other technique, is that no calibration is required. So, just like LDA here or PIV, here again you do not require any calibration, and that is the major benefit, because we have the system which is opaque, you have the system where the discrete phase fraction is very high. So, the calibration is the very challenging in this case, and we will discuss that how challenging the calibration is. And as I mentioned earlier, the technique wherever you require a calibration, the accuracy of measurement will be limited to the accuracy of calibration. So, these things can be neglected, you do not require any calibration, and that is the major advantage of the PEPT over the RPT. So, the advantage which I will say is that basically again it can measure all the 3 component of the velocity with the direction. It can map the complete velocity field. Even in the PIV, if you want to measure the complete column, if the column size is big, you cannot do it. You can focus to a certain area because that will be the only focal length available with the camera. You cannot go beyond it, but in PEPT you can measure the complete flow field. The problem is you are tracking only one particle at a time, so it will require a huge time to complete the experiments, but you can ideally track the complete flow field. You can measure very low velocity, you can measure very high velocity, but the only thing is you will be limited with the temporal resolution and spatial resolution. So, you should not be limited with that. Say very high velocity, your temporal resolution should be higher, so that you can catch each movement, you can catch you can have the data, neither the particle will move a very far distance between the 2 subsequent data acquisition time. So, temporal resolution need to be improved. So, within that temporal resolution you can acquire the data at a very high velocity. For very low velocity also you can use, the only thing is you have to be taken care that between the 2 subsequent time or 2 subsequent data acquisition, the particles should move certain distance which can be detectable. Okay. So, that should be higher, that one need to be do. The major thing is you get huge data set, and again we will discuss the importance of this data set while discussing the RPT. You can get the Lagrangian track of the particle, individual particle, that how the particle motion is changing, and major is, as we already said, that it can be used for opaque system, which the other 2 non-invasive technique which we have discussed cannot be used. The disadvantage, The detector system is very complex, it is a array of the detectors, the simultaneous detection is required. So, this is kind of a very complex detection system, and that make the cost of PEPT is very high, very high actually. And we will see comparison to RPT, this cost at least will be order of magnitude higher. Okay, it is very costly compared to RPT, which we will discuss next. The next limitation is that because you are generating, you are not using a gamma ray source, you are using a source which is generating the gamma rays. Because of the annihilation, the energy of gamma ray is fixed to 511 keV, and therefore, for a very big system or the system where the wall thickness is very high or internal thickness are very high, you cannot use it, your attenuation will be very high. So, your signal to noise ratio will be very low. So, therefore, that limits the application of this to not a very big system. Suppose if I have 1 meter diameter or so, the system accuracy will be hampered or system accuracy will be compromised. Okay. It has relatively lower spatial resolution compared to PIV and LDA. As I said that resolution goes in order of 1 mm. So, it is much lower compared to the PIV and LDA, which claims it has relatively lower temporal resolution compared to PIV, particularly once we are using a high speed camera or the 2 pulse mode, where the pulse time between the 2 pulse can be in the order of nanoseconds. And major disadvantage again is you need proper safety gadgets, you need TLD badges, you need proper dosimeter, you need area survey meter to monitor the radiation level around you, because you are dealing with the radiation. Then second thing, you cannot use this technique everywhere, you need to have a proper certification, you have to acquire the proper approval from the concerned authority. In India, that authority is Atomic Energy Regulatory Board. You have to get the certification from them that your laboratory is safe enough to use the radiation. You have to certify the lab. So, this is again the limitation. It is not like PIV and LDA that anyone can use. You require lot of homework, lot of work before you start doing these experiments. So, lot of approval will be needed. You need a trained person who knows how to handle the radiation and all. But major advantage which give the boost to this technique is that you can use this technique for opaque system, you can use this technique for opaque column. So, if the column is opaque, you can use it. If column is transparent, but system is opaque, like the fluidized bed I saw in the previous diagram, the figure, you can still use it because you are using gamma radiation. So, it can penetrate anything. That is the major advantage over it. Okay, so, next class whatever we are going to discuss, we will discuss about the radioactive particle tracking technique, and whatever the reconstruction approach or post processing approach we will use, we can use it here. Only the reconstruction of the particle here is generally done with the triangulation theory. We will discuss the different reconstruction algorithm there, but most of the post processing approach can be used for the PEPT also. Thank you.